So today we are going to talk about replacement series or substitutive experiments. Now, the purpose of these experiments is to determine the competitive abilities of the weeds and the crops at the same time. Now, one of the weaknesses of the additive experiment, which we discussed previously, is that it cannot determine the competitive ability of the crops. So the research questions which we may be interested in under replacement series experiments. Number one, what is the competitive ability of the plant species in a mixture? Or alternatively, we can rephrase this question and say, what is the competitive ability of weeds and crops? Now, let's look at the methods. In this case, we are interested in the species proportions, which have to be varied, but the species total is maintained. So we are talking about proportions of the weed and the crop, but the total will remain the same if we combine the weed and the crop. So in a mixture involving A species and B species, when A is increased from 0 to X, B is decreased from X to 0. I will further explain this with the numbers using two different types of experiments. Now here we've got examples of plant mixtures in replacement series. The first one is known as the binary structure. In a binary structure, we've got two plants, the crop, which is maize, and the weed, which is rapoko. Now, we should have our treatment will consist of proportions of maize and rapoko grass. Now, as we increase the proportions of maize from 0 to 10, we shall be decreasing the proportion of rapoko grass from 10 to 0. For example, the first proportion, we have 0 maize and 10 plants of rapoko grass. This could be in a pot. Next, we have 2 plants of maize, 8 of rapoko, 4 maize, 6 rapoko. Then there's a special treatment where everything is equal, where we have 5 plants maize, 5 plants rapoko grass. Then we can increase the maize to 6 and decrease the rapoko grass to 4. When we have 8 maize, we have got 2 rapoko grass. Then the last treatment is that we have 10 maize and no rapoko. Now, this treatment can be said to be soil maize. This one is a soil rapoko grass. And because we are using maize and rapoko grass, these are 2 plants. It's a binary structure. However, what it means is that we are only looking at one weed, but in reality, in the field there could be a lot of weeds. So let's see if we are having two more weeds, what sort of arrangement we can have. We call it the ternary structure. So in the ternary structure, we've got maize, rapoco grass, and the Mexican clover. Let's say we have got maize, 15 plants, rapoco grass is 0, maize, Mexican clover 0. Then we have a situation where maize becomes 0, rapoco grass is now 15, and the Mexican clover is now 0. Another treatment where we have 0 maize, 0 rapoco grass, and this time around we have Mexican clover. Then we have another set of treatments where we can have 8 maize, 2 rapoco grass, and 5 Mexican clover. In another round, we have 5 maize, this time 8 rapoco, and 2 Mexican clover. The third set is now 2 maize, 5 rapoco, and 8 Mexican clover. And of course, we have a set where everything is equal: 5 maize, 5 rapoco, 5 Mexican clover. And we can go on to have 6 maize, 4 rapoco, 5 Mexican clover. Then again 5 maize, 6 rapoco, and 4 Mexican clover. And the last 4 maize, 5 rapoco, and 6 Mexican clover. If you look closely at these numbers, they are balanced so that these 3 plants are equally represented in the proportions. But should we have 3, 4, 5 weeds, then it becomes very complicated. So in some cases, you'll find that the most reported experiments are the binary structure. So we're going to focus on the binary structure and see how we can determine the competitive ability of maize and rapoco grass. What is measured in these experiments is simply dry matter, biomass. Now, when you have got your data in the form of biomass, we want to examine how you can interpret the information or the data. Number one, we can use the replacement series diagrams. We can also use competitive indices. By the way, there are more than 50 competitive indices. But we are going to focus on the usually reported indices, which are A, relative yield, B, relative yield total, C, relative crowding coefficient, and the last one, D, which is aggressivity. Now we're going to start with the how we can use replacement series diagrams to determine the competitive abilities of the crop and weeds. Now, a replacement series diagram, it's like a graph which is represented, which is representing two plants. In this case, we have got plant A and plant B. And at the bottom here, we have got the A being varied from 0 to 1, and the B being varied from 1 to 0. It could be 0 to 100% or 100% to 0, depending on which plant you are looking at. So A and B have got these proportions which are on the x-axis. If we look at the response for A, where we are increasing the density of A, this is the dry matter yield. We expect this to increase diagonally. And if we look at B, as we are decreasing the density from 1 or 100% down to 0, we expect the dry matter of B to decrease in this direction diagonally. And this horizontal line is the relative yield total of A plus B. So in this situation, where we have produced these two diagonals, we can say A and B species have equal competitive abilities, because this replacement diagram is showing these two diagonals. In the second figure, we now have the diagonals being curved. If you look at the diagonal for A, it's curved away from the original position, and we call it concave. B also departs from the original going upwards. A is downwards, but B is upwards. We call this the convex shape. So if B is convex, it becomes the competitive. It's highly competitive compared to A, which is concave. So we can say B is more competitive than A. And in the second diagram, the situation is reversed. We now have A having a convex position. It's departing from the original diagonal. And B is now concave. It's also departing from the original straight line. Now, when A is convex and B is concave, we say that A is more competitive than B species. Then we come to a situation where everything is concave. If you look at A, it's concave. It's also departing from the original diagonal line. And the B is also departing from the original diagonal line. Now, this situation where we produce two concaves for A and B represents antagonism. It means A species and B species are antagonistic to each other, and the expected the relative yield total A plus B is also concave. And this shows us that there is no productivity, or the productivity is very low. The contribution of both species are very low, which means they are antagonistic to each other. This may represent aridopathy. Then we have a situation where everything is concave, convex, sorry. So B is got a convex position. It's departing from the original diagonal. Also, same applies to A. Uh, this is supposed to be a straight line, so we have this convex. So this indicates that when you mix the two plants, production goes up. This shows symbiotic relationship. But I must say that as far as the weeds and the crops are concerned, this is rare. It's rarely reported. Now, I want to give you an example where a replacement series was used. So it's in a paper entitled A Replacement Series Evaluation of Competition Between Rice Oryza sativa and the rice barnyard grass, which is a weed. The objective of this experiment was to determine which rice cultivar tolerated the Echinoclea oryzicola, which is a weed. So they used replacement diagrams. You can see these two replacement diagrams from this paper. This variety is called the Hashen and is represented by these triangles. And this is the weed ECPH represented by this rectangular shape. And this is the total. These are the varieties, the Delaman, and we have the same weed ECPH, Echinoclea, and this is the total. Now, if we come to this replacement series graph, here on the y-axis, we have something representing probably yield. And these are the proportions of the wheat and the rice to the wheat ratio. Where you have got 100, it could be wheat, rice, you decrease it to 75, 50, 25, then 0. And the wheat started 0, 25, 50, 75, and is increased to 100. Now let us look at the behavior of Hashen. You can see this is the graph for Hashen. It is departing from the diagonal. So it is convex, and at the same time, the weed is departing from this diagonal straight line. It's curved downwards, and the rise is curved upwards. So when you have such a situation, we say a Haitian has got a convex shape, and this weed has got a concave shape. So Hashem variety rice of Hashem is actually more competitive than the wheat. If we examine the Delaman with this uh, triangle, it is actually the okay. Hang on. Hashem has got this uh, curve which is below the diagonal. So it means it is actually less competitive. And this should be the width, which is more competitive. So sorry about that. It's actually the width, which is more competitive here than the this variety. So when we come here, it's actually Delaman, which is more competitive because it's it's above this diagonal, and the width it may not be clear. Sometimes it's along this diagonal, but as we move up, it's now below the diagonal. So it's slightly less competitive. And this uh, rice cultivar, if we're going to make a choice, I think we would choose Delaman because it would tolerate the echinoclora wheat. So this is how we use these replacement series diagrams. So you may have to read that paper and see what the authors are saying. We have also one paper which is looking at the relative competitiveness of irrigated rice cultivars and this weed, Ashkinameni dendiculata. Anyway, I don't know this weed. We don't have it. Anyway, let us see the replacement series diagrams. Now you can see everything is concave. Here we have got the relative yield total, which is far away from the diagonal. And also, this is the diagonal, and you see how concave it is, right? So it means that the situation here is terrible. We have got serious antagonism. Here again, we have serious antagonism. This one is slightly better, serious antagonism here, and there as well. Again, a lot of examples of antagonism demonstrated by this paper. Maybe you may have to read it and find out what is going on. I think there are some varieties which are being screened for tolerance to weeds. Probably all the varieties were not performing well in this paper, but you may need to read it. Also, another paper on the competitive ability of bean cultivars with the hairy beggar ticks. Hairy beggar ticks, I think it's Biden's pilosa. I think it's one of the common names for Biden's pilosa. So this paper looked at different bean cultivars against Biden's pilosa. Probably they wanted to find out which bean cultivar could tolerate this wheat. Again, probably you would agree with me that this is another disaster as well, because we have antagonism here as well. Antagonism here as well. Everything is concave. Here again, concave. Everything is concave. I don't think there was any bean which was useful here against the competition for against Biden's pilosa, because we had, I think they had an allelopathic situation where Biden's pilosa could produce chemicals which could affect uh, the bean, and the bean also in reverse produced something which could harm Biden's pilosa. So nothing good is coming out of this situation. Very interesting. Maybe you need to read it. Here we've got a study which was done in Zimbabwe. Competition of soybean with blackjack, Biden's pilosa, another paper, but looking at soybean and pigweed. This was done by Chivinge and Schwepenhauser. What they concluded was that pigweed was more competitive than blackjack. Rupende in 1997 also studied the Rapoco grass and found it to be more competitive than Mexican clover. And in these two studies, replacement series diagrams were used, and they had to come to these conclusions. So I want to summarize information which we can get from replacement series diagrams depending on the outcomes. It depends on the plants in the mixtures. The first scenario where you have plants A and B, this is relative yield, these are the proportions. If you have got straight diagonals and you have this line above relative yield total, it means A and B have equal competitive ability. And when you have this situation number 2, where A is convex and the B concave, it means A is more competitive than B. Then another scenario where you have now B being convex and A being concave. It means B is now more competitive. Then the scenario which we revealed in those papers, where there's antagonism, everything is concave. Uh, so this situation reveals antagonism. This one, which represent symbiosis when everything is convex, is quite rare. But you can see this one was being reported in across papers. And also this situation. Here we've got another experiment, I think, Acanthospermum hispidum with the soybean. You can see a lot of production. This is the relative yield total. Maybe you may want to find out which is more competitive Uh, Acanthospermum hispidum or soybean. Anyone who wants to attempt this one? Are you there?
Yes.
Which between acanthospermum and the soybean, which which plant is more competitive than the other? Blue represents soybean. This brown represents the acanthospermum hispidum. I don't know whether it's looking blue or brown from your end.
What about the green one?
The green one is the relative yield total.
Oh, okay. Um, soya is more competitive.
Yes, I think so. Although that acanthospermum, it's half half. Okay. Anyway, this is the idea. Anyway, you have got the idea, which is good. Now we move on to the other parameters. We can use relative yield of the crop, which is defined as the yield of the crop grown in a mixture divided by the yield of the crop in a pure state. Conversely, we can also use the relative yield of the weed, which is equal to the yield of the weed grown in a mixture divided by the yield of the weed in a pure state. And also the relative yield total, that was the horizontal line which we saw in the replacement series diagrams. So relative yield total is equal to relative yield of the crop plus relative yield of the wheat. Now, values, relative yield total values, what do they mean? If it is one, probably that's where you see that horizontal straight line in the replacement series diagrams. It may mean the wheat and the crop have equal competition. If it is less than one, wheat and the crop are antagonistic. Above one, there is synergism or symbiosis. Now, another parameter which can be estimated is relative crowding coefficient, or in short, RCC. We can compute the RCC for maize in a mixture like this. You take the value of the maize yield in the mixture and divide it by the yield, by the biomass or rapoko yield in the mixture or the wheat yield in the mixture. Then you keep that figure. You also take the maize yield in a pure state where there are no weeds, and you measure also yield of the weeds in a pure state where there is no crop. So in this case, it will be the rapoko yield dividing into maize yield in a pure state. You keep this figure. Then what you get from the right, here, you divide it into what you get from the left side. Then you get your value with respect to maize. You can do more or less the same thing with the Rapoko, where you find RCC for Rapoko, like this. Rapoko yield in a mixture divided by the maize yield in the mixture. You store that value on the right. You divide the Rapoko yield in the pure stand by the maize yield in the pure stand. You keep that value, then you divide that value into what you get to the left. So the right value is divided to the left value. So when you have done that, RCC values, uh, they may they may be equivalent to 1. In this case, maize and Rapoko have equal competitive abilities. If it is more than 1, it means one of the plant species in the mixture is more competitive. It could be maize or Rapoko. Less than 1, one of the plant mixtures in is less competitive. It can also be maize or Rapoko, depending on which equation you have used. Remember, there are two equations, one with respect to maize, the other one with respect to Rapoko grass. So this one is calculating a value with respect to maize, that one a value with respect to Rapoko. Aggressivity is another parameter. Now, it is represented by AGR. So we can calculate AGR for the crop and AGR for the weed. For this example, we have AGR maize, which is equal to 0.5 relative yield of maize minus relative, actually 0.5 multiplied by everything in the brackets, relative yield of maize minus relative yield of Rapoko. Then we do the same for Rapoko, AGR Rapoko. It's equal to 0.5 multiplied by everything in the brackets, relative yield Rapoko minus relative yield maize. Now the values which we get, if we get a 0, it means that the plants in the mixture have equal competitive ability. And if the value is positive, the value could be positive or negative rather. High AGR means a strong competitor, and vice versa. Now, the disadvantage of this approach is that we can only use one density because our proportions should add to one density. Let me go to the treatments. Now, if we look at our treatments here, the density is 10. We can only operate at 10. 2 plus 8 is 10, 0 plus 10 is 10, 4 plus 6, 10, 5 plus 5, 10, 6, 4, 10, 82, 10, 10, 10. So this is the one density which is being referred to because we are only using one density. In this case, it was just 10. What if in the field there are mixtures with the proportions with the 20, 30, 40, 100, and so on? Is our study going to explain what is in the field? And the answer may be no. So this could be the one of the disadvantage because we cannot extrapolate what we get from one density to other densities, which means that there's a need to modify these approaches. So I am going to explain a sort of a hybrid experiment, which involves additive, a combination of the additive design and the replacement series design. And it's quite a complicated design known as the addition series, complete factorial, response surface. These are some of the terms which are used. So the replacement series can be improved by including many densities in one experiment. The response surface diagram is used to interpret the results rather than a replacement series diagrams. Here we have got the response surface diagram. The disadvantage is that this is likely to become a very big experiment, like what was explained by Swanton in 2015. Maybe I'll give you the title of the paper. Now, this is an example of the addition series experiment. Let us look closely at the treatments. If we look at the first five, you can see that Rapoko is decreased from 100 to 0, and at the same time, maize is increased from 0 to 100. And we are operating at 40, which is the total density. The next set of treatments starts from 6 and ends at 10. We were doing the same with Rapoko, starting from 100 going to 0, and starting with the 0 maize going up to 100. And we have now 60 as the total density. We go again to 11 to 15. We are starting at 100, going to 0 with the Rapoko, then 0 to 100 with the maize. And we have these proportions adding up to 160. In fact, if you want, we've got two factors. One is density with the 3 levels. And we have got proportions, which are 5 proportions. Was 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have got a 3 times 5 factorial if you wanted to explore the design. But this is the treatment structure. So it's a 3 times 5 factorial, which you may replicate maybe if you are doing a pot study 6 times, and you can get biomass data and do and interpret the information. Now, as far as interpreting the information from such studies is concerned, I may have to introduce a concept relating to the effect of density on yield, so that you may, once you get that concept, then we can talk of interpreting what we get from this kind of study. So we've got a small journey uh, in trying to understand the relationship of yield and density. So effect of plant density. If we have density on the x-axis and yield on the y-axis, as we increase density, let's say this is maize population. This now is an intra-specific competition. We increase the density, yield is increased up to a certain point. In some cases, when we are doing agronomic studies, we have certain plant populations for maize, for groundnuts, for soybean, according to agroecological regions, according to how rainfall patterns are experienced. And we can match densities so that we reduce intra-specific competition so that we can maximize grain yield of our crops. So this typical example is actually commonly used by agronomists. And this is the kind of the regression which describes this graph in a monoculture. So Y is the yield of crop in monoculture, D is plant density of crop in monoculture, BO is the intercept, BC is the slope. So this equation is describing that graph, this graph. Density is represented by D. Anyway, you don't need to worry much about this equation, but if you look at this graph, it makes sense. When you increase density, you increase yield. But anyway, there comes a point when this becomes flat. In another way, we can write it like this. Now, in this case, we're looking at all the plants in a given area. If we look at the individual plant weight or contribution, as we increase density, the curve is like this. Probably let me explain it a bit. When an individual plant is on its own without competitors, it can produce maximum biomass or grain yield. If you add other plants to compete with it for nutrients and light, the yield starts going down. As long as you are increasing density, it goes down, and you end up with this curve. But if you are looking at the plants together contributing to yield, you get this sort of curve. And we can make this a straight line. If we plot a graph where we find an inverse of individual plant weight, or we divide this weight into one and plot it against the density, this is what we get. So 1 divided by individual plant weight gives us this straight line. Now, there are two interesting points on the straight line. There's this one which is the intercept of the graph. This one is the slope of the graph. And we can write this is the reciprocal. I mean, if we divide it into one, it's a reciprocal, sorry. So we can write an equation which is a straight line. 1 divided by the individual plant weight, or the reciprocal of the plant weight, is equal to BO plus BCD. D is the density from this axis. So at least we now know how an individual plant can behave during a competition. At the University of Zimbabwe, there were 2 studies done on Tithonia rotundifolia and Erycina indica in maize. One in 2012-13 by Miyaradzigata, and the one in 2013-2014 by Tabu Nyakurai. Now, this is the Tithonia rotundifolia density. This is its biomass. You can see the graph looks like the first one. We were increasing with density, and the yield is on this axis. And the yield is almost increasing. It's like this graph. You increase density and you are measuring biomass as yield, you get this sort of shape. So you can have this shape. If you now divide this weight into 1, or you find the reciprocal of this weight, you now get this curve, which demonstrates that at this position, an individual plant can maximize yield because there's no competition. But as it experiences competition, you get this sort of curve. And if you plot like what they did, 1 over Tithonia biomass, a straight line was produced. Just like what is happening here. So it's a true reflection of what happens in competition. And 1 over Tithonia biomass becomes a straight line equation. Now, this sort of concept was advanced by Peters in trying to understand competition in addition series experiments. Now, this is the first equation. It's like this one here, where you have a crop on its own, and you have 1 over WC equals to BO plus BC DC. This is a monoculture where there's only maize. Now there's a situation where you have a crop and a weed. We can still advance this concept and describe the situation there like this: 1 over WC, this is the individual weight of the crop, is equal to BCO, this is the intercept, plus BCC, this is the slope. So this is the slope. DC is the density of the crop. BCW is the slope of the weed, and the DW is the density of the weed. We can also do the same with the weed, where 1 over WW representing the reciprocal weight of the weed. So we can have BWO, this one represent the intercept, then BWW slope, DW density, plus this belongs to the weed. For the crop, BWC representing the slope, DC representing the weed. You can see here we have brought this whole term here across to here. No, no, it's not the whole term. So this represents the weed, this represents the crop. Now, if we wanted to measure intraspecific competition, we just look for BCC and the BWW, same species competition. So these values will tell us something about the intraspecific competition. Then interspecific between weed and the crop, these values, BCW and BWC, will tell us something about the interspecific competition. So in this experiment, we can now measure everything. There are no limitations. We can go ahead and measure the competitive ability of the crop using these terms, which we obtain from the equations. BCC divided by BCW, that is the competitive ability of the crop. Then the competitive ability of the weed, it will be BWW over BWC. And there's something which we can also calculate as an extra parameter, which can be of interest to those who are doing ecology. It's known as the niche differentiation index. And those who do intercropping studies, sometimes they calculate niche differentiation index using now these terms. Now this term is multiplied by that term. Or you multiply competitive ability of crop times competitive ability of the wheat. It will give you the niche differentiation index. These are just parameters which are used to further understand addition series experiments. Now there's this paper which you may want to read. It's about this edition series experiment by Radovich. Now, this is these are the combinations which can be used in addition series experiments. For example, you can use, you have got two species A and B. So you can have one B, one A, 4B, one A, 8B, one A, 16B, one A, and so on. So you can use this sort of it's like a cross table where you can work out the treatments. Sometimes you can have too many treatments and you may have to reduce. This box represents the response surface. Here we have got proportions of maize and the rapoco. So it's a three-dimensional graph which is used instead of the replacement series diagram. Anyway, this is what it looks like. You may also read this paper about the addition series experiments, and it gives these three-dimensional graphs or response surface diagrams. And you'll find that the reciprocals of plant weights are now used in the equations. So what I was trying to explain is what you may get in these papers. So you may read this paper by Swanton. It it may try to explain what you are trying to learn. So these are you may get a better understanding from these papers. So this is another paper again on addition series experiments. Another paper again on the same subject. This paper again on competition of Imbirata and maize may be important. You will sort out what you think is relevant, but I think some of these may help you to understand what you are explaining. Like the last paper, competition and niche differentiation in barley and wheat mixtures under rain-fed conditions in the central highlands of Eritrea. So these are mixtures of barley and wheat. These are both crops. In intercropping, again, the technique can be used. So this is it about addition series experiments. I want to move on to dialer uh, experiments. Now, the ones which I have now talked about are the ones which are commonly used. Dialer experiments are rarely used by crop protectionists or agronomists. Now, the objective here is to find the competitive ability of two plant species. So, what is the competitive ability of two plant species? So, you have, let's say, plant A and B. A, it will be one plant. Then you have two plants, A and A. Then you have A and another different plant B. You can also have plant B and BB. So here we have got in intra AA and BB, then inter A and B. So you can measure intra specific competition, A versus AA, B versus BB, and also inter-specific competition. You can also compare AB versus AA and AB versus BB. So you are just using single plants. Probably this is just for academic interest. You may not probably apply this to crop fields. So I won't talk much about this uh, dialer experiments. Then the next is the neighborhood experiments. Now, for this one, you may want to find the effect of weed deposition on crop yield. Now, in a field, there are weeds which grow along the crop row and those which grow in between crop rows. Which of the weeds are competitive? Probably that could be the question. So the effect of weeds is assessed on the crop, which is the target species. The weeds are planted at various positions from the crop. For example, you can have weeds within the row, which is 0 centimeters. Then you can have some weeds in other treatments, 15 centimeters, 20, 30, 35, and 45. So we can use this diagram to try to comprehend the structure of the treatments. So we can have weed positions 0. It means the weeds are within the crop row. That could be treatment 1. And you can have weeds 15 centimeters away from the row, treatment 2, 30 centimeters, 3, 35, 4, 45, 5. And when you draw a graph of distance from the crop row and crop yield, as you are moving away from the crop row, crop yield is increasing. It means probably the weed here and the crop here are not interfering with each other. There was an experiment to this effect which was conducted at Henderson Research Station, where weeds were varied from 0. It means weeds were within the row, or they were at 20 centimeters or 40 centimeters away from the crop row. I think this was in maize. In the first season, there were no significant differences. But in the second season, you could see that maize yield, when you have weeds within the row, was about 3 tons. And if the weeds were far away from the maize row, it was increased up to 4 tons. And if they were at 40 centimeters, yield was at 5 tons, which means the crops at the weeds at 40 centimeters were not interfering with the crop. So this is a neighborhood experiment. You may also read this paper. Uh, I think it's also talking about the neighborhood approaches or something similar to it. Then we come on to nail the design. These are important for forestry studies. You know, when you are dealing with forestry studies, it may involve having large plots because you are dealing with the trees. So you need very large plots. So the nailed design can be convenient. So it is used in tree density plots. Maybe you want to find the plant spacing or the tree spacing which is appropriate. You can test multiple tree densities in a single plot. That is the advantage. You have circular plots containing concentric rings, and regression techniques are used to analyze narrowed wheel studies. So this is the kind of a plot which you can use. You can see in the towards the center, the density is very high of trees, and as you go out of the center, the density is less. So you can measure, you can take parameters starting from the inner circle going outwards, and you can have a special arrangement of sampling so that you have a statistical analysis. Here I have got two trees, ash and sycamore, represented by those two dots. You can see the red or brown dot represents sycamore. Ash is blue or green. You can see at the center there is high density, and as you move out, uh, the trees are spaced. So you can do measurements starting from here going outwards, and you can take things at random and do a proper analysis. So it is known as Neruda design. It's a wheel. So here it is showing how you can take your measurement from this wheel. Here we are showing the portion of the wheel. Here it is the actual photograph of the actual plots in the field. Here, this is the typical wheel or a plot showing, towards the center, there's high density. As you move out, spacing has been increased. And you can take this information from a single wheel. This is the aerial photograph of such a study. You can see trees in the outer space here and those which are in the center. And the measurements can be taken from the center going outwards, or trying to measure competition. This is an intra-specific competition. There are papers which I have added. You can read this application of narrowed wheel experiment design in forestry research. Also, another paper on the insights of the nailed design. Yeah, this will can also be applied to field crops, but probably it may be complicated. You may have to probably find some examples, but it's mainly in forestry. Now I will just summarize the lectures on weed density. We started by defining weed crop interactions. Uh, we we talked about probably competition at length, very brief on areopathy, interference, and the parasitism. We also looked at what plants compete for. Uh, we explored intra-specific competition, interspecific competition. Then we looked at the methods which are used to study the effects of weed density in crops, additive designs, replacement series designs, addition series or response surface designs. 1, 2, and 3 could be very important uh, for you because it can enable you to identify important varieties or identify problematic weeds. Then we have got diagram designs which may not be very useful to you. Neighborhood experiments, yes, you can use them. Neighborhood experiments, if you are in forestry, you are likely to employ these. Then we also highlighted indices of plant competition, things like aggressivity. This was proposed by McGill Christ. Relative crowding coefficients, it was initiated by DeWitt. Then relative yield total, replacement series, and substitutive experiments are also common in intercropping studies, maize, cowpea, or maize groundnut. You may want to have a look at that paper by Swanton. It may add value to what we have been talking about, or it may throw some light at some of the issues. If you want to know more about indices of plant competition, there's also this paper. Then there's this question which I put at the end, where I'm saying, is there scope for identifying maize hybrids with the trait to tolerate weed infestation for the low input agricultural systems? Maybe we may discuss it if we have time. Otherwise, this is the end. Let me stop presenting.